All right, guys, I wanted to give you another example. We're going to raise level of difficulty just slightly to apply Newton's second law. So here is our box again, and we are going to have an applied force, but rather than the applied force being purely horizontal, we are going to incline it at an angle. So this is going to be the applied force here. The angle is going to be theta, and the other forces acting on the object are gravity, which is the mass of the object times g, and normal force, Fn. There could be friction, but we're going to wait. First thing that I need to do is recognize my object is moving in this direction, so that direction is going to be positive. We can establish a coordinate system if we would like. This is x, this is y, this is positive x, and this is positive y. Now, once we've done those two things, I am going to break up my vectors into horizontal and vertical components. So the only vector that I need to do that with is applied force. So there is an FAPX here and an FAPY. Based on what we know from trig, FAPX is going to be FAP cosine of theta. Looking at our sign convention and our coordinate system, it points to the right horizontally, therefore it will be positive. For the y component, we get FAP sine of theta. It points vertically upward, and again, based on our sign convention, that is also positive. Normal force, positive. Gravity, negative. Once I have direction of motion, vectors decomposed, and signs put in place, I can write out F net equals ma in both x and y. So I will start, guys, with x. So we have F net x equals max. Keep in mind, we are being specific to what we are asking for. We are looking for the forces in the x direction, and that is going to give us the acceleration of the object in the x direction. The only force acting to move the object in the x direction is the horizontal component of the applied force, which is FAP cosine of theta. And so F net becomes FAP cosine of theta equals max divided by mass. Ax is FAP cosine theta over m. From there, let's look at F net in the y direction. The reason that we write out F net in the y direction, and I want us to get into the habit of doing that every time, is because when we talk about friction, friction depends on the normal force, and I can't get at the normal force without knowing F net in the y direction. So I'm going to start here. I'm going to get in the habit of doing this every time so that when we get to a problem where it really matters, we know how to do it. So looking in the y direction, instead of two forces like I had in the previous example, we have normal, we have gravity, and we have the vertical component of the applied force. So in writing this out, I have F normal minus mg plus FAP sine of theta equals 0. Now recall, all right, this object is moving horizontally. We established that at the beginning of the problem. Therefore, Vy is 0. As a result, acceleration in the y direction is also 0, so that makes this term, may, go to 0. Now, I could leave it at that, but I am going to, in preparation for beginning to start thinking about friction, I'm going to solve this for F normal. So we have mg minus FAP sine of theta equals F normal. Now, this expression should make some sense to you. If we only had mg here, so there was no vertical component of the applied force, then the surface, which is the normal force, would need to support the entire weight. But because my applied force has a vertical component, that applied force will support some of the weight, so normal does not have to support all of the weight as in the previous example. I hope this was helpful, guys. Next video is going to talk about friction. Thanks and have a great day.